Starting video 2 for magnetism, AP Physics 2 Cram. And we're going to look at torque. So we have a square loop here with current going in this direction, okay, counterclockwise, and torque equals BIA and then sine theta. And really, we could put an n in front of this equation, because if we wrap this many times, n is just how many times we wrap it, and it becomes a multiplier of it. Okay, well, let's first of all take a look at this. So we have magnetic field pointing in this direction. So this part and this part both, okay, they will, of course, be parallel or anti-parallel, so there's no magnetic force acting on them. So what about when we're going down and up around this way? Let's look at this way first. So we're going up here. So I put my right hand in the direction of this current. My fingers are pointing there. I've got to wrap my fingers in that direction. Therefore, we have a rotation into the page here. And this one's the opposite, so it must be coming out of the page. So this is going to rotate in this kind of direction, like this. Now, where does the BIA sine theta come from? Well, BI, of course, is the magnetic field and then the current. Okay, what about the A? Well, let's review. Force magnetic does equal BIL. Okay, and if we call this L, the length of this side here L, okay, and the length of this side here L, so let's draw a double arrow here. Okay, if I want the magnetic force acting on this, that's going to be BIL. But we need to remember that we are dealing with something that's spinning, so imagine an axis of spin going on here. Okay, and let's call this width divided by 2 then, the distance from here to there, and this will be the width. So if I want torque, then I'm going to multiply both sides of this by W divided by 2. Because torque is force times the distance we are to the point of rotation. Well, how far are we away? We are W divided by 2. Okay? But we have a force on this part and this part. So we need to multiply both sides of this by 2. And what are we left with? The torque is going to be equal to B I L times W, and of course sine theta. Well, what's length times width? Well, that's area, of course. So torque is equal to B I A and sine theta, and then of course an n. It's because we're not always going to be perpendicular to the field as something rotates. Let's take a look at another example of this to help us understand. Let's say I have a square loop of wire. So now let's go back to this. So now I'm looking at maybe this end of it through this way. So we're going to see the ends of the wires only here. So let's go back to this. So I'm looking at the end of the wire here and the end of the wire here. It looks like that one's going into the page. And this one's coming out of the page. So we're going to look at this as it rotates into all these angles here. Okay, well, the current's going into the page here, so I'm going to put my fingers going into the page. I'm going to wrap my fingers to the right, the magnetic field, and we see that we have a magnetic force pulling downwards here, and one pulling upwards here. So this is rotating in this direction. Now, because our field is at an angle, we need to use the sine of theta, okay, in order to get the actual torque on that. Okay, so we can kind of just imagine a little triangle here. I'll try to draw it on there. If this is theta here, then this is theta also here. The perpendicular component of that force is what's causing rotation to happen, and that's why we use the sine in this case. If you remember, torque is force times distance times sine of theta, back in last year when we were just doing mechanics. So there you have it. To get the perpendicular part, here's our hypotenuse, here's our angle, so that's the opposite side of the triangle. Okay, so we'll do BIA times the sine of theta. All right, now, what if we are located at this position here? Well, it looks like we're 90 degrees here. So now we have maximized our torque for this example, because all of magnetic field going this way is going to go straight into our force, and our force is already 90 degrees, so that's going to be our greatest. Now what about the loop continuing to rotate? And here we are, we're completely perpendicular. Okay, so now torque is going to equal 0 since the angle is 0. So we are perpendicular to the field, and our forces are actually going to be going outwards, trying to stretch that loop. That's not going to cause spinning. And of course, now we rotate in this direction here a little bit farther, and we get negative torque. Okay, so how does that happen? Well, look in here. We have current going in that direction there, still. And force will now be downwards on that, still. So it's going to cause rotation backwards now. So this loop is going to go back and forth, back and forth, back and forth. So that's why when we built our DC motor, we actually had to change what was going on here to always keep the the current going in this direction on the right side and the current coming out at the left side. And that's what the brushes of our motor did. It kept the current going in the right direction, or the correct direction, to keep us constantly spinning around, not going this way, that way, this way, that way. Okay, so that's torque. And our next topic is the solenoid. Okay, so first of all, let's talk about N in a solenoid. N is the number of turns per unit length. And our equation for a solenoid is going to be B equals mu naught N times I. Okay, where N is the number of turns, mu naught is our permeability of free space, the 4 pi times 10 to the minus 7. Okay, and of course, I is the current. Well, what would N equal for this particular solenoid? Well, I've got 1.5 centimeters, and how many turns do I have? 1, 2, 3, 4, 5, 6, 7. So N is going to be capital N, which is 7 turns, divided by length L, which is 0.015. So we're going to get turns per meter. All right, now let's say our current is going in this direction, and it goes in a circle like this, and then around and around and around and around. So what direction would magnetic field be going in this case? Well, let's take the one circle going like this. We're going to point our thumb in the direction that the current is going, and our fingers are going to wrap this way. So it looks to me like each circle is going to have an X here in the center of the circle. So that means magnetic field for all of these circles is actually going to be going and down in this direction. Okay, so imagine that we have circles of magnetic field going like this over here, and like this over here. Let's do this wire here. This one will be going like this. And of course, this one will be going on this. Okay, and I should probably complete the circles like this. Okay, so what's going to happen is we're going to get a additive effect of magnetic field going like this inside this solenoid. And that, of course, will produce a strong north here and a strong south here. So the magnetic field would then wrap around like this. And it's kind of a messy diagram, but hopefully you get the idea. So a solenoid is just loops right next to each other, and the magnetic field is an additive effect. Just increases and increases. That's where that N comes from. And the higher the turns per length and the higher the current, the greater the magnetic field will be generated by the solenoid. And typically, we also add a piece of metal in the middle of these guys in order to magnify that magnetic field. Metal is probably iron. Okay, that's magnetism video 2, or AP test, AP physics cram video number 13. Another video coming up for magnetism soon.